In this video, we will discuss how to demodulate an amplitude modulated signal. How an amplitude modulated signal is generated has been discussed in another video, which you can see. So we'll see how to demodulate a double sideband suppressed carrier signal first. For that, demodulation of a double sideband suppressed carrier signal essentially involves multiplication by a carrier signal and is identical to modulation. So what we do at modulation is we multiply the carrier and the message signal, and so we get the amplitude modulated signal. During demodulation, we multiply the received amplitude modulated signal again with the carrier signal that should have the same frequency and phase as the incoming carrier, which is AM signal in this case. So the product is then passed through a low pass filter. For demodulation, the receiver must generate a carrier in phase and frequency synchronism with the incoming carrier. These demodulators are synonymously called synchronous or coherent or homodyne demodulators. So the block diagram of this demodulation process is shown here. So this is the amplitude modulated signal at the input that we want to demodulate. This is the carrier signal, the local oscillator, which has the same frequency omega c as the frequency of the incoming AM signal. After multiplication, we get the signal ET. That signal is represented by this expression. So you can see we have cos square omega ct. Now using a trigonometric identity, this cos square omega ct can be converted into half 1 plus cos 2 omega ct. So the square is removed and twice the frequency appears here. So as you can see, this part of ET can simply be low pass filtered to get the baseband or the message signal at the output, because the frequency 2 omega c is very high. It's much higher than the message signal, so this can be easily removed at this point. And so this is how we simply obtain the demodulation of an amplitude modulated signal. The ET in the frequency domain looks like this. So this is the expression for the frequency domain of ET, where you can see this part is the message signal spectrum, which can be filtered out. Now if we look at the demodulation in through this spectral plots, so that's how it looks like. The spectrum of ET is the expression is this, and the spectrum is shown here. So you can see the components, frequency components at 2 omega c appear here, and this is the low frequency signal, which is our baseband message signal. So we can simply filter it out, and this is the so we filter it out, and this is the message signal after the filter that we obtain. Right, so this was demodulation of a double sideband suppressed carrier signal. Now we then have seen in the video that we can also generate a full AM signal, where the carrier is sent along the double sidebands. So how do we demodulate a full AM signal? If you remember, a full AM signal has it basically, what we do during full AM modulation is that we clamp the message signal, to such a level that its negative excursions do not exist. So that is the same when we multiply this signal with the carrier, then we get a full AM signal. Now, like DSB SC signals, full AM signals can also be coherently demodulated. So this coherent demodulation is almost possible. It works for almost all the modulation schemes. But as we have discussed, coherent demodulation defeats the purpose of AM, because it does not take defeats the purpose of full AM, because it does not take the advantage of this additional carrier that we are sending. So we add this A to the message signal, so that the message signal is clamped. Its negative excursions do not exist. They are actually taken towards the positive side along the y-axis, and so that's how a full AM signal is generated. So the purpose of full AM signal is to get rid of the locally generated carrier. Now the modulation index, if it's less than or equal to 1, the envelope of the full AM signal follows the message signal. Right, so we shall here we shall consider two non-coherent methods of AM demodulation. So this method, where we multiply the carrier, is called a coherent method, and now we'll see two non-coherent methods of demodulating a full AM or an AM signal, which satisfies this condition where the modulation index is greater than 0 and less than or equal to 1. So the two techniques are rectifier detection and envelope detection. So these are the two non-coherent methods that we will see. So this one is the rectifier detection technique. So here you can see this is the circuit for the technique. The full AM signal appears at the input. We have a diode. Now the signal at this point is shown here. So this is, as you can see, the full AM signal. No part of the message signal, the envelope of the message signal, is towards the negative side. So no part exists in the negative zone. So that's why we can see it's a full AM signal. Now the signal at this point, after the the diode, we have only the positive part of this signal, which is this one. So what it does is the diode rejects the negative cycles and it only allows the positive part of the signal. So effectively this is the signal that we have after the diode. Now you can see the carrier is still there. So this is still a high frequency signal. So when we pass it through a low pass filter, we get a signal like this at this point. So the after low pass filter, you can see the carrier is removed and we are left with the only the message signal, the clamped version of the message signal, which means that A is still added, it still exists with the message empty. So this is the DC component, as you can see, and we can remove this DC component by using a capacitor, as you can see here. So the signal at this point after the capacitor is shown here. So this is the message signal empty, and we can always adjust the amplitudes according to our requirement. So now you can see the negative part of the signal is also shown here. Right, so this technique is called the rectifier detector technique. Effectively what it means is that through the rectifier detector technique, we are multiplying the AM signal, which is this one, with a series of rectangular pulses. As you can see, this WT represents the rectangular pulses here. So a periodic pulsed signal is being multiplied with the full AM signal. So this is the voltage at the resistor across the resistor VR. Now the purpose of this discussion is to show, on the previous slide we saw that rectifier detector can work theoretically by looking at the different components, but how would the expressions of this circuit work? So it's as if, because the diode is switching the circuit on and off, so it's as if we are multiplying a rectangular signal with the full AM signal. So when we do that by applying a trigonometric identity, the Fourier series coefficients of a rectangular signal are mentioned here. So these are the Fourier series coefficients of a rectangular signal. So when we multiply it with the full AM signal, you can see there is a DC part in it. So that DC part can be taken out, right? Or in fact, apart from this DC part, this cos omega CT is being multiplied with this cos omega CT. So this becomes cos square omega CT. And by using the trigonometric identity that we saw previously, for coherent detection, the cos square can be converted into cos 2 omega ct, and so that's why we can take out this signal from the higher order frequencies which are appearing here 3 omega c and 5 omega c. So this is the mathematical proof that the rectifier detector can give us the message signal at the output. So just to summarize it, when VR is applied to a low pass filter, the voltage across the resistor is applied to a low pass filter of cutoff B, the output is, this is the output that we get. All other terms in VR of frequency is higher than B. B is the bandwidth of the signal, right? So they are suppressed. The DC term, this one, may be blocked by a capacitor as we saw, and so we are left with only this term at the output. The output can be doubled by using a full wave rectifier. We used a half wave rectifier in the previous figure. If we use a full wave rectifier, the value of the output, the magnitude, can be increased, doubled. The high carrier content in AM ensures that its zero crossings are periodic, and the information about the frequency and phase of the carrier at the transmitter is built in the AM signal itself. Right, so the next technique, as we said, we will be discussing two techniques. The next technique is the envelope detector. As the name suggests, it detects the envelope of the AM signal. So this is the simple circuit for the envelope detector. The AM signal is applied here. We have a diode, capacitor, and a resistor which are in parallel. So now what the parameters of the circuit should be chosen based upon these criteria. So the RC, the constant RC of these two components should be much greater than 1 over omega c. So omega c is the carrier frequency of the AM signal, but this RC constant should be less than 1 over 2 pi b, where b is the bandwidth of the signal. Now the bandwidth of the AM signal depends upon how quickly the message signal MT varies. So if it varies quickly, then the bandwidth would be high. So that's why the RC constant shouldn't be very high, because if it is high, then the discharge or time of this circuit would be very large, right? So it should be high so that it can ignore the quicker variations in the carrier frequency. So that's why we have this frequency omega c in this relation, but it should be smaller than 1 over 2 pi b, so that it can at least detect the less quicker variations of the MT, the message signal. So this is the reason we have this relation over here. Now the output of an envelope detector follows the envelope of the modulated signal. On the positive cycle of the input signal, the input grows and may exceed the voltage across the capacitor. When this happens, the diode is turned on, and so the capacitor starts to get charged. So now the capacitor starts it becomes charged, and at that point, if the input falls below this maximum charge or maximum voltage of the capacitor, when it falls below this peak value, the capacitor starts to discharge, because and it discharges through the resistor R, right? So that's why the discharge time depends upon the RC time constant, right? So it discharges through the capacitor R, so we get a waveform like this. So this is the peak charge. So as soon as the voltage starts dropping, so the capacitor slowly discharges, and then on the next cycle of the AM wave, the capacitor charges again, and so we have a sort of a ripple sort of a structure which effectively follows the envelope of the signal MT. So the slow capacitor discharge through the resistor allows the capacitor voltage to follow a declining envelope. Capacitor discharge between positive peaks cause a ripple signal of frequency, so omega ct at the output. So we saw that because there are positive peaks in the AM signal, so the capacitor discharges in this way, right? So there are these ripples in the output voltage, and of course those ripples has the same frequency as the frequency of the incoming AM signal. This ripple can be reduced by choosing a larger value of RC time constant, so the capacitor will discharge slowly, but we have to make sure that this time constant is not very large, so that it at least follows the overall envelope variations in the envelope, which are much smaller, which are much slower than the variations in the carrier signal, right? So picking RC too large, however, would make it impossible for the capacitor voltage to follow a fast declining envelope. So it must follow this envelope, right? And so because of the maximum rate of AM envelope decline is dominated by the bandwidth. So as I mentioned, the envelope of the AM signal depends upon the bandwidth of the message signal, how quickly the message signal varies, right? So the RC should follow this criteria, the RC time constant. So it should be greater than 1 over omega c, so that the variations in the carrier are ignored, but it should be less than 1 over 2 pi b, so that the variation, the slow variation of the envelope is not ignored, because we want to follow the envelope. So in other words, from this expression, we rearranging gives us this value. So we know now the RC, what should be the values of R and C to get this expression. So as you can see, it depends upon the carrier frequency as well as the bandwidth of the signal. The envelope detector output is VC, it's equal to A plus MT, and it has a ripple of frequency omega c. DC term A can be blocked out, as we know before, that this can be blocked out by a capacitor or by simply using a high pass filter, so that low pass frequencies such as DC signals can be neglected. The ripple may be reduced further by another low pass RC filter. So in this video we have discussed the demodulation techniques of an AM signal. So if the AM signal is double sideband suppressed carrier, then we can use the coherent demodulation technique. If the AM signal is a full AM signal, then we have two detection techniques. One is the envelope detector and the other one is the rectifier detector. So both of them can be used. If you have any questions related to the video, then you can ask in the comments section. And finally, please subscribe to the channel to stay updated with the upcoming videos. Thank you.